Welcome back to my channel. This is Shadi Atia, professor at Liège University in Belgium, and today's lecture is about confidence intervals. Well, this lecture is the final lecture about the playlist of experimental research, and therefore it's very important to make sure that we will discuss the topics of quality assurance. Well, the content of today's presentation is mainly an introduction, discussing the 3R principles, how to calculate your confidence intervals in your sample, and how to check the robustness of your results overall before some takeaway messages. So let's start with an introduction. Experimental research is mainly an evidence-based research. And in general, science, in this sense, is seeking the truth. And truth is the first point of distinction between knowledge and opinion. And in the age of social media and democratization, and everybody can give their opinion, it's very important to avoid this noise and make sure that we are seeking the truth. Facts do tend to prevail at the end of the day, so you need to be patient and you need to have a vision. And our knowledge increases by gradually building over time. So it is never a big breakthrough. It's difficult to make big breakthroughs. It's most of the time incremental work, incremental effort, and based on that we can reach breakthroughs. In science, it's also important that the law of nature and not the law of market that we should follow. So it's important to mention this so that we are very focused and that we are avoiding the conflict of interest. Well, the market economy, why I'm talking about the conflict of interest, the market economy frames science that that its values and privileges can be monetized. And this is a problem because research has to generate money and fundraise, so the scientific world became a place where everyone is trying to attract attention. And in this context, scientists must remain objective and avoid the conflict of interest by the financial backers to make sure that the research are seeking the truth and producing results and facts that can bring us or make us closest to the truth. In this sense, if you want to have a look at the research ethics video, it can give you some insights about research integrity and explain this concept more into detail. Now, in this context, it's important to seek conclusive evidence. It's very difficult to produce conclusive and comprehensive evidence, and in general, evidence can be having ranges of quality and confidence. And what we have to do in our research is to reduce the doubt, reduce the experimental error, reduce the uncertainty of our work, reduce the impact of disturbances, influences, and erroneous factors, and for sure distribute the effect of noise factors more evenly in a random way to make sure that we seek the highest level of conclusive evidence. Now allow me to start with this concept of the 3R. Maybe we saw this concept together previously in some presentations, but the 3R is a very important concept that is mainly and fundamentally respected in the experimental research. And it is mainly talking about randomization, replication, or reproducibility and reduction of noise. And as you can see, blindness is also one of those aspects. Some people name it or list it as a separate criteria. I consider blindness part of the randomness or randomization. And in any situation where we want to investigate a cause-effect correlation, we must take into account these 3R and we must look at them into detail. But allow me to go one by one and start with the reproducibility. Well, why is reproducibility important of your research? Reproducibility is the repetition of an experimental condition so that the variability associated with the phenomenon can be estimated. And when we report this information in our methodology section, whether we are reporting in a report or a publication, a full description of the statistical parameters and test and description of the used techniques in the methods section should be included. So it's very important, and you can look at the method chapter where I'm talking about the importance of explaining and making your text written in a way allowing others to reproduce your work. Now some people get confused between reproducibility and replicability. Well, what is the difference? Well, reproducibility, which I'm seeking here in this lecture, is the successful reproduction of the original data by independent reanalysis using the same analytical approach and using the same data set. And this is very important to allow it to happen. If you are conducting research and having the opportunity, or if you believe in open science and you can share your data set, then somebody else has to be able to reproduce the work using the original data. However, when we talk about replicability, it's a different concept. Replicability is successfully finding the same or similar result in a new sample. So here we are talking about a new sample, totally new sample, and this is called replicability. And as you can see, Zach Scott said that good reproduction is about finding middle ground between replication and irrelevance, because at the end of the day, it will influence your research question, your data set that you are using, the methods and models that you are using, the instrument that you are using for testing, and for sure the researcher can be also different depending on if you are doing replication or reproducibility. And my advice to you in this sense is to use the round-robin test. What is a round-robin test? It's an experimental methodology to determine reproducibility of a process where tests are performed independently multiple times and the results are analyzed statistically to assess their variability. And I have a lecture about it, you can look at it. It was just the lecture before this lecture, where you can see an example here. A sample is analyzed and its properties is measured by the same or different laboratories using same or different methods, and finally we do an ANOVA or analysis of variance to make sure if this test has passed the round-robin test or not. So don't hesitate to look at the round-robin test as a way to assure the reproducibility of your work and improve the external validity of your work. Now the second aspect, or the second R, which is reduced noise, or in other words, control. Why is it important? Because it aims to minimize the impact of dependent variable and highlights false positives, signaling whether an update is more effective than the original. And here it removes the confirmation bias or the tendency to force the hypothesis into the results, and therefore I was talking about the conflict of influence and the importance to distinguish the truth from an opinion, to make sure that you are having a very serious approach to control your experiment and make sure that you are neutralizing as much as possible any extraneous factor. And in general, when you describe your methodology, a description of the comparison procedure and the comparison of the number of treatments that you did with single control, for example, the Dunnett test, can be done to prove that you are having a high control of your experiment conditions. This makes me move to the third R and the last R in this presentation, which is relevantly, strongly related to the confidence interval concept. Well, why is randomization important? Randomization permits the use of probability theory to express the likelihood of chance as a source for the difference between outcomes. It will make you able to establish a cause and effect relationship, and randomization will allow you to have all treatment will have the equal chance of being allotted to different experimental units. So in science, randomized experiments are the experiments that allow the greatest reliability and validity of statistical estimates of treatment effects, and randomization-based inference is especially important in experimental design and in survey sampling. And to make sure that you are having this randomization aspect, you will have always to communicate your confidence interval. Now, when we do statistical and we report statistic, a description of the randomization and the statistical test that were performed is very important. So this increases the transparency of your work. And in general, you need to describe your blinding that was done so that you make sure that blinding and randomization are well addressed. Now, before closing this section of the 3R, I need also to tell you something else. Well, if we are seeking conclusive and comprehensive evidence by conducting our experimental research, well, we need to also be aware about the different level of evidence. Randomization is the highest level of evidence. It provides the highest level of evidence and it can assure it. And as you can see, this is a list of different studies and types of studies regarding the levels of evidence. Number 1 is the highest level, and number 6 is the least level of evidence. And as you can see, the least level of evidence is that you rely on expert opinion. Somebody told you. Even if it's a medical doctor and an expert in a field, a PhD, a professor, an expert opinion is the least level of evidence considered by scientists. You will ask me then, what is then the highest level of evidence? The highest level evidence is to have a meta-analysis of randomized controlled trials. So you have trials, a lot of trials that were done in a randomized and controlled way, respecting the 3 R's that I was talking about, and those data sets are published, and somebody took these data and started to do a meta-analysis among those data sets to get a conclusive and comprehensive evidence. And this is one of the most expensive, tedious, and time-consuming or costly research that is available and requires huge teams, it requires access, and therefore you can see that a difference between an expert opinion and a meta-analysis of a randomized control trial is a huge difference, and it can take you in a totally different direction if you are seeking advice or informed decision making. So it's important to look at this table and always memorize it, that the lowest level of evidence is expert opinion, followed by case series or poor quality cohort case control studies. Level 4 is the systematic reviews of case control studies or simply case control studies. The level 3 of evidence is individual cohort studies and low quality randomized control studies plus systematic reviews for those cohort studies. Second level, or the second best level of evidence, is individual randomized control trials with narrow confidence intervals, not very huge, and systematic reviews of randomized control trials. So this is the second level of quality. And finally, the top quality of evidence where I can be assured and I have a sufficient comprehensive and conclusive finding is to do meta-analysis of randomized control trials. So it's very important to talk about it because, as you can see, the confidence interval popped up in level 1 and 2. And this brings us to the third part of our lecture, confidence intervals. Well, what are confidence intervals? Well, as you know, if we are having our experiment operationalized, designed, and performed, we start now to collect the data and analyze it. And in order to do that, we need to have our statistics ready, and we need to have the conclusion, draw the conclusion from the experiment. And the validity comes when we start to assess the validity of our experiment and how far is our randomization successful. And here comes the role of confidence intervals. To evaluate, they are used to evaluate the accuracy of my results simply. And as you can see, when we talk about confidence intervals, we need to already make sure that we have a population for our test. And this population is the group of elements or subjects, whether they are people, samples, materials, objects, the researcher wants information about. This is the large population. And then we have a sample representing this population, which is simply a part of the population the researcher takes out to examine and draw conclusion from. And the sample used to draw conclusion from the population is not always perfect. And as you can see, this means that I will take my population. In this case, for example, I'm taking lithium button batteries. I am having a sample representing a huge pool of this population. I'm doing my testing, and definitely by default, once I did a sampling, I will have sampling errors and I will have confidence intervals associated with my testing or my measurements for these samples. And I will need to report these confidence intervals. If you want to have an idea about statistics and how to do sampling, I advise you to watch a previous video about statistics for experimental research. Now, sampling error is simply the variation due to sampling. Because the sampling was only a selection of objects from the population, sample 1, 4, 3, 4 is a part of the larger one, it will never be perfect representation of the population. There will be always a sampling error. And what I need to do is to report the sampling error by calculating the confidence interval. So what is the confidence interval? A confidence interval is simply communication of how accurate are the estimates likely to be. And in this sense, I need to calculate the median of my population equals, and not only do that, I need to go beyond that and take the median for the population and define it in a range. So it needs to lie between an upper and a lower value. Once I communicate the median within this range, then I have a confidence interval. And as you know, the narrower the confidence interval, the higher the quality and the evidence, and the wider the confidence interval, the more I have less confidence in the results. Let's take this example here. I'm trying to verify the long-lasting battery life claim. I have here confidence interval distribution. This is a lower confidence limit. This is an upper confidence limit. This is the sample effect size. If I only report the median of the population, it doesn't say anything because it is not relevant. It's not comparative. While when I report the median for the population within a certain range, mentioning the highest value and the lowest value, then I can have a higher I have a more valuable information, and the confidence interval is the median within a certain range in this case. If you want to calculate the confidence interval, you have to follow this formula, the confidence interval formula, which is simply the mean of your sample plus minus the critical factor multiplied by the standard deviation. If you want to know what is the critical factor, I advise you to read this description. Very simple. You have already Excel sheets that can embed this equation, and from there you can start to calculate your confidence interval. Now, what affects the width of my confidence interval? Why I'm concerned with the width of my confidence interval? Because as I told you, if the confidence interval width is narrow, I have high conclusive evidence. If the range is wide, then I don't have high confidence. And there are three aspects that influence the width of my range for my confidence interval. Number one, the variation of the sample, which simply, the more I have variance, the narrower my confidence interval range. The lower I have variance, the wider the confidence interval range. Number two, the sample size. It's always recommended to have a larger sample size to make sure that I have a higher representation, and by consequence I have a narrower range for the confidence interval. And number three, and the last one, is the elimination of the co-founding variable or variables, so to make sure that I have distributed the confounding parameter or influence on the different samples. So the narrower the confidence interval are, the surer we are, and the larger the confidence intervals are, the less sure we are. And by that, once we calculate it, we can say or contextualize our result within a context. Because when it was just a number, a median number, it was meaningless. It's just not telling what is the upper, what is the lower. But once we give those two additional values, the upper and the lower range values, we can better contextualize the outcomes, and we can better understand how accurate and how representative is our testing and our sampling process. Now let me take you to the final part of the presentation before the takeaway message, talking here about robustness. I advise you, since I'm talking here about the last lecture in the playlist on experimental research, is to be very curious and increase your awareness about the importance of investigating the robustness of your research in general. When I'm talking about robustness, I'm talking about two aspects. First of all, internal validity, and the second, external validity. Now, internal validity relates to how well a study is conducted, how did we do the randomization, how did we select the sampling, how is our protocol and measurement protocol respecting best practices, how our lab equipment are calibrated, and so on and so on. And external validity relates to how applicable the findings are in the real world. How can I generalize, how can I transfer this knowledge outside the context of the experiment? So first of all, to check the internal consistency, internal validity describes the extent to which a cause and effect relationship established in a study cannot be explained by other factors. And here we have to look that our results are not biased, and therefore my number one advice is to calculate the confidence interval. Because if your study is not randomized, you cannot calculate the confidence interval. So the number one that assures that you have a randomization and you have an ability to make sure that your results are meaningful is to randomize your sampling approach and your testing approach and calculate your confidence interval. The second aspect in order to assess the robustness of your research is to look at the ability to reproduce your work. So here I would say perform a reproducibility study, not a replication study. Here we are talking about the assessment of the validity of applying the conclusion, or external validity simply assesses the validity of applying the conclusions of a scientific study outside the context of that study. So here we ask ourselves, is the result valid for other cases? And here I strongly advise you to run the round-robin test that we talked about. By doing this round-robin test, doing the same test and using the same samples in other laboratories and comparing results, you are making sure that you are validating your work externally. So my final advice for you today is to close this experimental research series by conducting confidence intervals via randomization for your randomized work, and doing reproducibility of your results, if possible, by the round robin or other tests that can assure the external validity. For sure, you will have in any journal a request for report your summary, and they will have a special section called statistics. As you can see here, statistics. And as you can see, I selected this text from the Journal of Nature Research, and I highlighted the sentences that are very relevant to what I was talking about. For example, you are requested here by Nature to indicate whether the same sample was measured repeatedly or not. Here I'm talking about reproducibility. Here I'm talking about the round robin test. You are requested by the journal to indicate the associated estimates of uncertainty, which is, in another word, confidence intervals. So what I'm talking about. And finally, you have to report with confidence interval, the effect size, the degrees of freedom, and the p-value that is noted for your work. So by that, you can see that also journals, they are requesting this information. Reproducibility and confidence intervals are very important, or the randomization are very important. So consider the confidence interval as a proxy for randomization, and consider the round robin test as a proxy for reproducibility. This takes me to the end of the presentation of today, and some takeaway messages before leaving you. First of all, we try to explain in this presentation what are confidence intervals. Well, confidence intervals communicate on how accurate an estimate of a parameter of the population is likely to be. I advise you to calculate the confidence intervals for your results. For every experiment, don't forget there is a perfect human bias. So we are trying by randomization and by blindness to avoid these human biases. And don't forget that we might also have conflict of interest because our funders putting pressure on us or framing our research, not allowing us to explore or seek the truth. Variation of the sample, its size, and the confounding variables influence the confidence interval values. Those are three important parameters that you need to look at, and if you really want to influence your confidence interval, you have to play with these parameters and to vary them. Randomization assures there is no confounding, but imbalances in covariates could arise by chance, so this also happened. And for sure, use the confidence interval formula that I indicated, that can be available also online, very simple, and based on that you can calculate it yourself. And my final advice is seek statistical training courses that help you better calculate your confidence interval values and understand this concept in general and apply it in all your research to make sure that you can have valuable, conclusive, and comprehensive results of your work. By that, I end up today's presentation. Don't hesitate to share the presentation as you find it valuable. If you have any complementary information, don't hesitate to fact check what I'm saying. If you wish to ask questions, don't hesitate. The comments are open. So I wish that you engage with the content and share it with other people. By that, I end up the time series, the lecture of today on confidence interval, and the playlist on experimental research. Thank you very much for bearing with me till now, and I hope this presentation was beneficial. This presentation was about confidence intervals. Thank you very much.